Yeah.
Oh, it's too much.
You know, picking up trash is one thing, but when your porch breaks, it's like I'm assuming. I mean, I don't know for a fact they're renting from it. Like, they don't own it. That's the reason they're coming down.
Okie dokie. Hi everybody. So today I'm going to be talking about linked lists. This is actually part of the series I've been doing for the breakfast bashes in the morning. This was the third installment of the thing where I talk about data structures, and this was the third one, and the recording got messed up, so I'm re-recording it now and presenting it to everybody because Travis thought it was good enough to redo. So yeah, it's cool that everybody's here. Basically, what a linked list is, it's a set of elements in sequence, and you have a front pointer and a terminator, and each element physically links to the next element in the list. So you start at 1, go to the next pointer to 17, to the next to 6, and then to the next to the terminator. The terminator a lot of times is just omitted from the diagrams because basically all it is that once you reach it, you're done traversing the list. So that's the idea there. And we'll talk about like the kind of operations that you can do with a linked list here. So the first thing that you can do is insert a new element onto the beginning of the list, which is pretty simple. And to do that, you basically create a new element or a new node of the list with whatever element you want in it. And then you move that front pointer to point to that, and you set the next pointer of the newly created node to the old front of the list. And then you have a new list. The next thing is remove beginning. So also very simple. Basically, move the front up to the next pointer from the beginning, and then destroy the link between those two nodes, and then finally just remove the node, release it from memory or whatever. The next thing is insert after. So you can imagine that you might want to put an element between 17 and 6, and that kind of thing should be possible. So we can insert nodes arbitrarily wherever we want into the list. To do that, we're going to insert 12 between 17 and 6. So starting at 17, we remove the next link from 17 to 6, and we create a new node with 12 in it. Next, we modify that next pointer from 17 to point to 12, the newly created node. And then from 12, we add a new pointer, the next pointer from 12 to 6. And that completes it. So now we've successfully shoved 12 in between 17 and 6. What's up?
Why wouldn't you first start with 12 pointing to 6 as well? That's moving 17 pointing from 6 to 12. So it's probably more beneficial.
You can do it either way.
I mean, basically, you're breaking it apart. You said you were removing the link.
Yeah.
I mean, maybe it's exactly the same thing, but
It is exactly the same thing.
It is the same thing.
Yeah, if I'm understanding you correctly.
Well, yeah, I mean, like when you described it, you're taking it off.
Yep.
Then you're pointing to that. Then you point to that. Whereas, what if you start by having 12 point to 6, both 17 and 12 are pointing to 6, and then move 17 to point to 12?
Yeah, it's the same. It's the same
thing,
thing.
I guess.
I think if you're implementing, you probably do it that way. In case you've got other things running in memory and they're accessing that list, that doesn't break the list.
Right. Yeah. Yeah. I mean, yeah.
As far as the integrity of the list, doesn't matter which way, but if you're actually implementing it, do it that way.
Yeah. Right. Yes. Good point. So the next thing that we can do is remove an element from the list. So we just inserted 12, and now we'll remove it. The first thing is to basically break up the next pointer from 17 and the next pointer from 17. Those are going to get removed, and we add we change the next pointer to point to the next thing from 17, and we delete it. I'm going to get rid of the node. And those are basically the four operations on singly linked lists that are pretty important. I'm not going to talk about this really at all. I was not planning on doing a breakfast bash on doubly linked lists, but I just wanted to mention that there's a pretty standard extension to singly linked lists, which is a doubly linked list where instead of just pointing forward, you can also point backwards. And this lets you kind of traverse a list in either direction, and it makes some things easier. So, and the last thing I want to talk about is an algorithm that we can use these singly linked lists to perform in a pretty cool way. So this is called merge sort. And the idea is basically to sort this list in ascending order. It's a pretty standard sorting algorithm, and I'm just going to work step by step through how we would do it with a linked list. But first, we need to talk about what it means to merge two lists together. So first off, you have to have two sorted lists already to make this efficient and make it worthwhile and make it work. But the idea is that you can traverse the list. You can kind of pick pieces as you go and place them into the list in sorted order. So we're going to look at that in more detail here. So the first step here is to look at the first two elements of each list. And since 1 is greater than -1, we're gonna look at the next element. But now, since 1 is less than 28, we know that 1 needs to be placed before 28. So really here, I should make a note that we're looking at like the next pointer to -1, really. But it's just easier to visualize this way. So because this is less than 28, we need to insert it after -1. And we can use our insert after operation to do that. And so we've done that. And then we do this again, and 17 is, again, less than 28, so we need to insert it after 1. And the benefit to this is that you're never going to make more than n comparisons. So if you have two lists, and the total sum of the size of them is n, you're never going to make more than that many comparisons, which is a good thing. You don't have to double up on anything, which is very common in sorting algorithms. Okay, so how can we use this to actually sort a list? The first step is to, the idea basically is that we're going to break the list into two lists until we get down to single node lists. And then we're going to merge everything back up in the way that I just described. So the first step is to find the center. We're going to remove the pointer and split it into two separate lists. One list, two lists, red list, blue list. And then we're going to do it again. Now we have 4. And we'll do it again. So now we've got 4 centers. And now we're almost done. We just have one more center to remove and produce 2 separate lists done. And so now we successfully kind of recursively split this thing into a whole bunch of different nodes. And the next thing that we need to do is take these pairs, all of these pairs here, and merge them together in the same way that we did before. And I should note that like the invariant that the lists be sorted that we were trying to preserve with the merge operation is sort of trivially true here because each list here is actually just a single element, so it's sorted already. And that's kind of the base sort of point for the merge. So now we're going to merge like crazy. So the first thing that we do is we take the thing at the bottom and we're going to merge that up. And that gives us the sorted list 9 and then 28. And then we're going to do the same thing with all of these pairs. And when we move up, we're going to pair the thing to the left of it with it. So does that make sense, everybody? Like, we merged the list, and now we're just going to merge that was the one on the next level up. So we'll merge all of these. 1 and 17 gives us the list 1 and then 17. -1's less than 6, so we switch those. -8's less than 201, so we switch those. And then with this last one, finally we're actually merging a list with more than one element. So we get the list 9, 28, 172 in sorted order by merging those two. And from here, like, we're basically just going to do the same thing over again. Again, we're just going to pair up the lists in the same way that we did before and merge them together. So we'll start with the one on the left. We get -1, 1, 6, 17. And then we'll do it again with the other side, and we get -8, 9, 28, 172, and then 201. And now we've just got two lists left to merge. And once we finish that, we put everything together, and the list is sorted. This might seem a little bit overly complex, but the reason is that it's an extremely efficient sorting algorithm. In the right circumstances, this is actually the most efficient sorting algorithm, and that is because of the fact that we have that merge operation, and it only needs to traverse the elements one time. In a lot of other sorting algorithms, you're going to have to, on each iteration, traverse 2 times or more. So, yeah, that's it. That's all I got. Any questions? Okay, cool. Thank you.
So would you use like a bubble sort, be a different sort of sort algorithm that would use, like, that would be much less efficient, I guess, right?
Yeah.
I don't even know what a bubble sort is. I know it just swaps values back and forth all the time. So.
Yeah. So bubble sort is less efficient.
But it would
than
use a
merge
linked list
sorts.
sort of, that would be another sorting algorithm.
But you could, yeah. Yep. That was actually the first thing that I was thinking of doing, but then I thought merge sort was more interesting. So, what's up?
I have a question, probably a dumb question, but so on the last merge from like the 2 arrays into the final array,
Yeah.
like 17 of course goes into the middle of the other array. So in that process, they're going to be breaking up of that other array in order to get 17 in there, or is that something that automatically happens or something?
We did the merge algorithm we described earlier. So the merge algorithm basically takes the head of each and kind of like iterates through it until it figures out where they all go.
Yeah. So if you work through this step by step, which I didn't do, just because of a time constraint mostly. If you work this out step by step, doing the same merge algorithm that I mentioned at the beginning, that's what would happen.
Okay.
Yeah. So, all right, cool. Thank you guys.
Thank you.
Now, yep.
If everybody wants to come